This morning, the discovery undersea of a large section of the Space Shuttle Challenger, which exploded more than 3 decades ago.
We have a report from the flight dynamics officer that the vehicle has exploded.
The hard sacrifice that was made by the crews of Space Shuttle Challenger in Columbia will now be shared with people.
The ocean kept the Challenger's secrets the way it keeps everything else. Quietly, patiently, under pressure and darkness, letting metal corrode and memories soften while the story above the waves hardened into something familiar. Most people know the outline by heart. A bright Florida morning, a shuttle climbing cleanly into blue sky, a sudden branching burst of white and orange that looked from far away almost like a strange kind of bloom. What's less familiar is the thought that the wreck itself might still be speaking, not through dramatic new pieces hauled from the seabed, but through patterns in what was already recovered, photographed, cataloged, and stored. Patterns too faint, too complex, or too scattered for human eyes to stitch into a single warning. That is where a modern kind of scrutiny becomes unsettling, when an AI-assisted reanalysis treats the Challenger debris field like a dataset and finds a signature that doesn't fit the story everyone thought was complete. Before we start, hit the like and subscribe buttons for more exclusive news. Challenger was not one object that failed in one simple way. It was a system of systems, and when it broke apart, it produced a kind of mechanical confetti spread across sky and sea, each fragment carrying a small record of forces and heat. Human investigators have always relied on those records, but the mind is forced to work with limits. People sort, group, and compare with a mixture of intuition and method. They focus on the parts already suspected to be important. They interpret scorch marks and fractures with experience and physics, but experience can also become a set of grooves, channels worn into thinking by what is expected to be found. An AI model doesn't get tired, doesn't lose track of an outlier after hours of catalog work, and doesn't care which subsystem is supposed to be the villain. It can be trained to look for correlations across thousands of photos, metallurgical notes, recovery coordinates, and telemetry traces, then to ask a simple question that is emotionally loaded in hindsight. What if something began deviating earlier than anyone proved, and the wreckage has been quietly consistent about it all along? The disturbing anomaly in an AI-style finding often isn't a single smoking gun. It's the kind of thing that becomes visible only when many small facts are stacked on top of one another until the stack leans unmistakably in one direction. Imagine the model ingesting high-resolution scans of recovered solid rocket booster joint hardware, close-ups of internal insulation, exterior paint blistering, and soot patterns. Imagine it pairing those images with time-synced film analysis from launch cameras, not to spot the obvious plume everyone already knows about, but to measure brightness gradients, flicker frequencies, and the geometry of smoke ribbons at the edge of resolution. Then add the debris field map. Where pieces were found, their mass and shape, what kind of tearing they showed, whether they carried marine growth patterns consistent with time at depth, and how they were oriented when recovered. Put all of this together and the anomaly takes shape like a fingerprint. A consistent asymmetry that suggests not just that something failed, but that it failed in a way that was already evolving, quietly, directionally, before the moment the world saw the catastrophe. One plausible and deeply unsettling signature is an unexpected distribution of thermal damage around the booster field joint that doesn't align cleanly with a single sudden blowby. People tend to picture a leak as a binary event: sealed, then unsealed, intact, then burned through. Real seals don't behave like that, especially under vibration, changing pressure, and shifting geometry. An AI looking across thousands of joint surface images could detect a repeating arc of subsurface charring or a thin crescent of erosion in insulating material that appears on multiple fragments from the same region. An arc that implies intermittent gas intrusion earlier than the final breach. Not a raging torch visible to the naked eye, but a repeated whisper of hot gases that found a path, retreated, found it again. That kind of pattern is easy for humans to miss because it looks like noise when seen one piece at a time. Seen as a statistical field, it becomes a map of heat that has direction and rhythm. If that rhythm is real, it changes the emotional texture of the event. The failure stops being a sudden betrayal at 70-something seconds and becomes a process that was already underway, an argument between materials and forces that began in the first moments of ascent. Solid rocket boosters generate enormous pressure and vibration. The joints that connect booster segments must remain sealed while the steel casing flexes and the joint geometry shifts. When temperature is low, materials respond differently. Elastomeric seals can become less resilient, putty can behave less predictably, and the timing of how quickly a seal seats can drift. In a system that depends on milliseconds and micrometers, small delays matter. The anomaly suggested by a subtle, repeated thermal trace is that the seal may not have achieved a fully robust condition when it needed to most, and that the system may have been flirting with failure in a stuttering way before it ever committed to it. There is another layer that makes such a finding disturbing. The possibility that the leak's earliest behavior could have been detectable, not necessarily by a human watching live, but by instrumentation patterns that were present and unrecognized. AI models excel at multi-signal pattern detection. Tiny deviations in pressure oscillations, vibrations, or temperature sensor noise that correlate with visual microflicker in camera footage. If a model reports that a particular set of oscillation harmonics consistently rises and falls in step with a faint brightening at the joint region in several camera angles, it suggests the leak had a personality, an identifiable signature, before it became catastrophic. That doesn't mean someone should have seen it on a monitor and stopped the launch in real time. But it does mean the data may have carried a warning that only now, with modern analysis tools, looks like a warning at all. The wreckage can also tell on direction. Hot gas escaping through a compromised seal doesn't just burn, it pushes, it erodes, it jets like a cutting tool. The AI might identify that erosion patterns on adjacent structures, nearby insulation, attachment hardware, or even paint ablation on neighboring surfaces, have a consistent vector. Humans can recognize directionality when it's obvious, but when you're looking at many small pieces, each with its own damage history and recovery context, the direction can blur. A trained model could infer a dominant jet direction from the elongated pitting, the tear lips on thin metal, or the way soot deposited more heavily on one side of a bolt head than another. If that dominant vector is slightly different from what was assumed in earlier reconstructions, it implies the jet was not simply a straightforward torch aimed where everyone thought. It could have been angled by joint rotation, by changing pressure, or by a transient seal that partially seated and then reopened, turning the leak into a moving hazard rather than a fixed one. This is where the anomaly starts to feel like it's pointing at complexity rather than blame. The popular memory of Challenger often condenses into a single failure mode and a few key decisions because human stories like clean lines. But a system failure can be both explainable and layered. A disturbing anomaly would be one that suggests there was not a single decisive moment when the system went from safe to doomed, but a period when it was in a precarious state, a region of time where the outcome depended on tiny contingencies. How quickly a seal recovered its shape, how the joint flexed under aerodynamic loads, how a plume was temporarily suppressed by reseating material, how vibrations opened and closed a microscopic path. AI analysis thrives in that gray zone because it can handle nonlinearity and conditional behavior in ways that traditional, more linear human reconstruction often struggles to keep vivid. The idea of intermittent sealing is especially unsettling because it creates the possibility of false reassurance. If a leak begins, produces a visible puff, then is partially sealed by debris, molten residue, or mechanical shifting, it can look like the problem went away. The system, in effect, stops screaming and starts whispering. Human attention is drawn to steady, loud signals. Intermittent signals are easier to rationalize as artifacts: camera noise, lighting, sensor drift. A modern model might identify that a particular puff-then-quiet behavior repeats in early ascent frames, with timing, that matches known structural loading phases. That repetition would suggest the system was cycling through danger and temporary stability, an engineering nightmare because it undermines confidence in any single snapshot of health. Even the debris field geometry can become part of the anomaly. When a complex object breaks apart, heavier pieces travel differently than lighter ones, and the timing of separation affects where they land. If the AI reconstructs that certain joint-related fragments show deformation consistent with exposure to high-velocity gas earlier than the main structural breakup, and those fragments are found in a pattern that implies they were liberated slightly earlier in the sequence, it suggests the failure may have had a more extended prelude. Again, not a dramatic extra event, but a subtle shift in when certain stresses became decisive. The disturbance here isn't in moving the timestamp by minutes, it's in moving it by seconds in a system where seconds are enormous. There's also the human factor in how evidence is interpreted. Traditional investigations do a heroic job, but they are also shaped by what is physically retrievable and by what questions are considered most urgent. AI doesn't change what is recoverable, but it can change the weighting of what's already present. A tiny fragment that was cataloged as miscellaneous insulation may become, in a model's eyes, statistically linked to a specific thermal environment and a specific location within the stack. A series of small, non-identical marks might be recognized as variants of the same process. The anomaly could be as mundane as a recurring micropattern, a particular kind of char edge that occurs only when hot gas impinges at a shallow angle for a short duration, repeated in several places where it shouldn't be if the leak was only late and only in one direction. That kind of shouldn't is what makes engineers sit up. What does it mean to say no one noticed before? It doesn't necessarily mean people were careless. It can mean the evidence was distributed in a way that required a different kind of synthesis. Human investigators are brilliant at deep, local understanding. This fracture looks like overload, that scorch suggests impingement, this residue indicates combustion products. AI excels at wide global association. This residue type correlates with that scorch shape, and both correlate with that location coordinate, and together they correlate with a small oscillation in telemetry. The anomaly lives in the intersection between local truth and global pattern. If the anomaly points to earlier onset of seal compromise, the implications reach into how high-risk systems should be monitored and how evidence should be preserved. One implication is that the most valuable warnings in complex engineering may be weak signals that only become meaningful when fused across domains. A faint brightening in a camera frame means almost nothing without knowing the precise geometry of the joint and the expected reflection from sunlight and exhaust plume. A tiny pressure ripple means little without understanding the vibration environment and the filtering behavior of sensors. But when those weak signals line up repeatedly, the alignment itself becomes information. This pushes toward a worldview in which safety is not only about designing robust hardware, but also about designing robust interpretation, systems that can detect and flag unlikely combinations of minor anomalies. Another implication is about humility and reconstruction. Every major failure investigation tries to answer what happened. It must, because without that answer, you can't learn. But there is always the danger that the first coherent answer becomes the permanent answer, and later evidence is forced to fit it. An AI finding that introduces a subtle but consequential nuance doesn't invalidate earlier conclusions. It enriches them. It says the event wasn't just a story with a single villainous moment, but a chain of interactions in which the system briefly balanced on edges. That matters because future systems can fail in similarly edge-balanced ways, where the difference between success and disaster is not a clear threshold, but a shifting landscape. The anomaly also raises uncomfortable questions about what counts as noticed. Engineers did notice concerns about seals and temperature and joint behavior. Those concerns existed, but noticing a concern is not the same as quantifying the exact failure dynamics in advance, and it's not the same as having operational tools that can reliably discriminate between benign oddities and true precursors. If AI can now detect an intermittent signature that correlates with joint compromise, the implication is not that people should have magically spotted it then. The implication is that we should build the ability to spot such things into the systems themselves. Onboard diagnostics, ground-based pattern recognition, and a culture that treats weak signal clusters as worthy of hard attention. There is, too, an implication about how we store and share investigative data. AI analysis thrives on rich, well-organized archives, consistent labeling, high-quality imagery, precise metadata, and access to the raw signals rather than only processed summaries. The Challenger wreckage record, like many historical records, is vast but uneven, created under pressure and shaped by the tools of its time. A modern reanalysis that finds a new anomaly is a reminder that preserving raw data is not mere bureaucracy. It is a gift to future understanding. The more complete the record, the more likely it is that later tools can find something that earlier tools could not. In high-stakes engineering, that can translate into preventing a future tragedy. It also forces a conversation about the limits of AI and the need for careful interpretation. A model can detect patterns that are real, but it can also detect patterns that are artifacts of data collection, differences in camera exposure, uneven photo quality, inconsistent cataloging, or recovery bias. The responsible way to treat a disturbing anomaly is as a hypothesis generator. If the AI flags a consistent crescent of charring, metallurgists and structural experts still need to validate whether that crescent truly implies early gas intrusion, or whether it could be explained by post-breakup exposure, by seawater effects, or by misattributed fragment origin. The implication is not that AI replaces expertise, it widens the searchlight. In the best case, it points experts toward places where the physical world might have been speaking quietly. What makes an anomaly like this linger in the mind is how it rearranges the timeline inside the same 70-odd seconds. The visible breakup is still the moment everyone remembers, but the event becomes less like a switch flipping and more like a narrowing corridor the vehicle is traveling through. In that corridor, the difference between contained exhaust and escaping exhaust may be measured in tiny seal motions and microscopic gaps that appear and vanish as the stack bends and straightens. If the AI pattern is pointing toward that kind of narrowing, then the failure point stops being a single dot on a graph and becomes a moving boundary, one that might drift with temperature, vibration, aerodynamic loading, and the dynamic response of the joint hardware itself. That matters because humans are naturally drawn to single dots. They're easier to argue about, easier to explain, easier to pin to a checklist. A moving boundary is harder. It demands thinking in ranges, probabilities, and evolving conditions rather than neat thresholds. That evolution also changes how we imagine the relationship between what the camera saw and what the machine felt. A rocket can be in distress in a way that looks calm from the outside. It can also be in trouble in a way that looks dramatic, but is, in fact, survivable if it is transient and self-sealing. If the anomaly suggests a repeating, faint signature early on, it reinforces the idea that spectacle is not a reliable proxy for severity. The most dangerous thing can be the thing that almost fixes itself, because near fixes are persuasive. They tempt observers into thinking the system has corrected, when the reality is closer to a wound scabbing over while pressure continues underneath. For any future high-risk system, the lesson is uncomfortable. A quiet moment after a small irregularity should not automatically be treated as reassurance. It might be a clue that the system is oscillating between stability and instability. A second implication is about how we define evidence when the evidence is statistical rather than singular. Traditional engineering proof likes clean demonstrations. A part failed here at this temperature under these loads. A machine learning finding can look different. It might say that out of hundreds of fragments, a cluster shares a texture and chemistry that rarely co-occur unless exposed to a particular kind of hot gas impingement, and that cluster maps back toward one region with high confidence but not absolute certainty. That kind of result can be deeply useful and deeply awkward at the same time. Useful because it reveals structure and chaos. Awkward because people crave absolutes when dealing with tragedy. The challenge is learning to treat probabilistic evidence with rigor, not as a hand-wavy suggestion, but as a quantified pointer that still needs physical validation. It asks investigators to become bilingual, fluent in materials and mechanics, and also fluent in distributions, confidence intervals, and model limitations. Model limitations aren't a footnote here, they are part of the implication. Wreckage analysis is an arena where bias can sneak in through the back door. The record is incomplete by nature. Some pieces are never recovered, some are altered by the sea, Some are photographed more carefully than others, and some are labeled with more precision. An AI can accidentally learn the quirks of documentation instead of the quirks of failure. If, for instance, certain kinds of fragments were more likely to be photographed under particular lighting or magnification, the model might over-associate those photographic features with a subsystem location. A disturbing anomaly should therefore prompt a discipline of adversarial checking, deliberately testing whether the signal survives when you remove confounding cues, when you scramble irrelevant metadata, when you compare across multiple independent data subsets. The implication is that modern investigations need not only smarter pattern finders, but also smarter skepticism, methods built to prevent us from falling in love with a compelling pattern that is actually a shadow cast by the archive. At the same time, the sheer possibility of finding a previously unrecognized signature raises expectations about what investigations should be able to do. That can be dangerous in its own way. If the public hears that AI can rediscover hidden clues in old debris, it becomes easy to assume that every disaster is solvable down to the last molecule, and that uncertainty is a sign of incompetence. But complex events often have irreducible ambiguity. Multiple physical processes can leave similar marks. Multiple timelines can fit the same scattered evidence. The implication is not that we can eliminate uncertainty, but that we can map it more honestly. An AI-assisted approach can show which hypotheses fit the data well and which fit poorly, and it can show where the data simply can't discriminate. That's a different kind of truth. Not a single story, but a landscape of plausibility. There's also an ethical implication in how such findings are communicated. A new anomaly feels like new drama, and drama attracts the human mind the way bright light attracts insects. But the real responsibility is to keep the focus on what the anomaly actually changes about understanding the event itself, the physics of the failure, the nature of the warnings embedded in the system, and the kinds of monitoring that might catch similar patterns in other machines. If communication tilts toward shock value, it can distort attention away from the technically meaningful part, like the difference between a one-time breach and an intermittent migrating leak. The implication is that modern analytical tools require modern restraint. The more powerful the lens, the more careful we must be about what we claim it shows. Otherwise, the lens becomes a spotlight used for theater rather than a lamp used for learning. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us? What are your thoughts on AI anomalies in Challenger Rec? We want to hear from you. Thank you for watching and see you next time.